on the left, a close-up view. Actually, I think that was done with the Hubble Space Telescope. So you can see, of course, that this milky stuff is really just the light of millions, actually billions of stars. But you can see that particularly the shorter wavelengths, the blue light, has been heavily absorbed by interstellar dust, and it's kind of patchy. It's like looking through clouds. Somewhere in there is the center of the Milky Way galaxy, but it's very difficult to see it. Unless you had a long wavelength of observations. Now, here's a better shot on the right. You can see there clearly is a center, and we're not at it, but the Milky Way does seem to wrap all the way around the sky. This is an all-sky projection, and that's because we're not at the edge of it, we're inside it. So, but you can see very clearly how flattened it is there. Then those are the two Magellanic Clouds orbiting around us. Even in this picture, you can see that there still is dust absorption, even at a longer infrared wavelength. But this shows you much better what the true distribution of our galaxy is. Now, the interesting question for today, though, is, okay, let's suppose that we can make detailed observations of this flat disk. What's it doing? Well, it should be controlled by what's the only one major force in the universe that mostly makes objects on large scales go. That should be graphed. The visible picture that I showed you on Wednesday. Here's a more revealing picture at longer wavelengths. So how is everything moving around? How large is the Milky Way, or in particular, how far away are we from the center of it? A great deal of effort went into figuring this out, and it's really difficult. It's a classic problem in astronomy, which I'm going to get into a lot more detail on in the last 2 weeks of the course. We have great information with our telescopes on Earth. We can't really move from Earth, just receiving light. We have great two-dimensional information about things all around the sky, even at very high magnification. But how do you know the third dimension? You look at a bulge of light like this. This is a cartoon of it. Here's the actual data. You look at this, a lot of stars there. This is starlight of billions of stars. How far away are those stars? Or putting it another way, yes, the Milky Way is a very flattened disk. Yes, we are inside it. That's how come we can see it in all directions. But how large is it? How far does it extend? Well, you would need to know the distances of objects. And getting the third dimension of objects, astronomical objects, is a classic problem in astronomy, which it's probably as big as almost any one of the other jobs that astronomers do. And we've been getting better and better at it. But you can see how difficult it's going to be. So I mentioned, for example, does anybody remember what the one method I told you that is the gold standard method if you want to know the third dimension, the distance, for example, of a star? How do we figure out the distance of the stars? You use the fact that the Earth moves around from one side of the sun to the other every 6 months. To basically, you have two eyes, you get a binocular vision, you see the parallax angle of the star moving back and forth. And the smaller the angle is, that must mean the further away the star is. That is brilliant. Unfortunately, that really does not, hardly really works for stars that are across our galaxy. The parallax angle is currently just too small for us to measure. You can sort of figure out what the angle is. You know, if the stars are thousands of parsecs away, then we're talking about parallax angles that are just thousands of 1 second of arc. It's just beyond our technology currently to measure that. So we use indirect methods, and the most popular indirect method would be to look at a bunch of stars in a star cluster, see how bright they are, and then find the main sequence of the star cluster. I'm not going to go on about this in detail. And then you'd say, well, if this main sequence is what I understand it, you know, that's kind of a universal. It's the same everywhere. In particular, for example, let's look at stars on the main sequence that are the same temperature as the sun. They must have the same intrinsic luminosity as the sun, right? So if I see how bright they appear to be, then I use my brightness luminosity formula, and I could work out, assuming that those stars are the same as the sun, I could work out how far away that star cluster is. And that basically is how this scale was put onto this picture. It took a long time. Where's the center of the Milky Way? Well, it's where this largest concentration of light is. And even though the visible light is very well blocked. The longer wavelength light comes through pretty clearly. Anyway, this direction of the center of our galaxy happens to be fairly far in the southern hemisphere. It's in the constellation of Sagittarius, which we'll get back to. And currently, actually, this is a little bit out of date. I think the best estimate now is that the sun, that means our whole solar system, is about 25,000. 25 is probably a little more accurate than 28, but who cares? I'll give you full credit on the exam, from the center of the Milky Way galaxy. So this is the center of mass of the system. So that's where the center of gravity is. So, shouldn't we just fall in? You know, this is where most of the mass is. Shouldn't the sun and the solar, you know, the planets, everything going along with it, just fall right in? Actually, this reminds me a little bit of a question we had earlier in the class. How come the Earth and the planets don't just fall right into the sun? The sun is where the center of mass, the center of gravity for our solar system is, but we do not fall in at all. The answer is the same in both cases here. It's also the reason that the solar system is never going to fall into the center of the Milky Way. Whatever the gravity is in the center of the galaxy, it's mostly stars. There is a black hole there also, which adds a bit. It doesn't matter because we have a great deal of sideways velocity, and our spin, our angular momentum, our orbit has to be conserved. There's no friction on the sun, so it's going to keep on orbiting around here in approximately a circle at approximately a radius of approximately 25,000 light years. It is not exactly a circle. In fact, it's not even exactly an ellipse, because the gravitational mass, you know, is distributed in a more complicated way. So sometimes we get a little bit closer to the center, sometimes we're a little further away. It might vary from, you know, 15,000 to 30,000. I don't remember the exact numbers. All right, so, but that's right. We are orbiting around the Milky Way galaxy. Now that immediately raises an interesting idea. So it sounds like a similar idea to when we discovered, you know, that the planets are orbiting around the sun. What was the interesting idea? Let's measure the speed of the orbit, because what would that tell us? Now, I'm just going to use Kepler's, well, they're basically Newton's laws of gravity here. If I could measure the speed or the period of the sun's orbit around our galaxy, what would that give me information about? It's pretty much the same formula. That would tell me, that would show how much we're being accelerated by the gravity of the Milky Way out at this distance. We need to know how big our orbit is. So we need to know this distance from us to the galactic center. And then if we knew that and we knew how fast we were going, we could figure out what is the gravitational mass of the Milky Way galaxy. You see, that's, man, I've done this several times in the course. We also use this method to figure out the masses of unseen stars in binaries. Remember, neutron stars and black holes. I mean, I've got a limited playbook here, but we keep playing astronomy's greatest hits here. Find something you can measure its Doppler shift, measure its acceleration, infer how much gravitational acceleration is moving it, figure out what the mass is that's causing it to orbit around. Right? We've done this over and over again, and we're not finished yet. We're going to do it, I think, like 2 or 3 times in this class. What would it look like, by the way, if you could get outside of the Milky Way? I'm sorry, this is probably a somewhat realistic picture, not of the Milky Way. Of course, we've never been able to send any spacecraft to look back down on, we're in the plane of the Milky Way, but it would probably look something like this. There's evidence that it's a spiral galaxy, has these beautiful spiral arms. We're not at the center here. We're not at the edge here. We're sort of maybe about halfway out here at 25,000 light years. The Milky Way does extend. You'll notice that this is all galaxies, the concentration of stars, the concentration of light, the concentration of mass is way highest in the middle. And like any sort of sensible object, as you get further and further away from the center, the density goes down, it thins out. There's less of it, but there's still stars out here twice as far away from the center of the galaxy as we are, out at 50,000 light years out. So people ask me sometimes, if they're in the mood to ask, you know, well, how big is the Milky Way there? That's not a simple question to answer, right? Because it just keeps on extending, probably even further than, okay, this is not a picture of the Milky Way, but how big is this galaxy? It's probably bigger than this picture. Actually, it just keeps extending to lower and lower density until it becomes hard to measure. In some sense, some galaxies practically almost extend with very thin, low density of matter, practically until you get to the next galaxy and its halo. Anyway, but okay, so I can't tell you everything about that, but at least if I could measure one object or just a few objects that are orbiting around the center of the galaxy, then at least I can tell you how much mass is included inside their orbit. Suppose that they're going approximately around in a circle. Now, the reason this galaxy doesn't look circular is because it's tilted. It is a circular disk, but it's viewed at a random tilt. So that's why it looks kind of more elliptical looking. Here is a face-on spiral galaxy. So again, this would be a view if you could look down on the Milky Way and look back at it, there would be the center of it. See these beautiful spiral arms. We're probably on the edge of something of a spiral arm, maybe about halfway out, maybe about out here somewhere. If we could look at the Milky Way, we'd see something like that. So how would we figure out, though, how long it takes for us, actually the orbits go in this direction, turns out. So how long would it take, or how long does it take our sun, our solar system, to go once around the Milky Way? Well, we know how big the trip is. It's 25,000 light years. So let's see, if that's the radius, if we're going roughly in a circle, we'll go with that approximation. Then if the radius is 25,000, then what's the circumference of our orbit? Be about 2 pi times that, which is about 6. So it would be about 150,000 light years. Man, that's quite a big trip that we're making just to go once around our galaxy. Let me just read the chat questions here because these look interesting. I always like the questions here. Yes, you could go in different directions around the galaxy. The fact is, though, that most everything here in the spiral galaxy like the Milky Way is going roughly approximately in circles, and they're going mostly in the same direction. Probably for the same reason that most of the stuff in the solar system is mostly going roughly on circles and mostly roughly on the same direction. Why do you think that is? It's allowed. The laws of gravity would allow it to go in an opposite direction or in a highly elliptical orbit. I think the answer is right here. Things would collide, things would smash into each other the same way as happened in the early solar system. So after a few spins around, the stuff that's not going on approximately circles in the same direction would have collided into something else and maybe been destroyed or altered. That's probably what happens when a galaxy settles down into a disk also. Very nice question. Galaxies probably do not start out in flat disks. The same way that like when a star is formed out of interstellar gas, it's probably not in a flat disk either. For the same reason that a star forms a planetary system due to gravitational collapse, for that same reason, when a much larger mass of gas collapses to make a galaxy, it's likely to settle down into a rapidly spinning disk where things are mostly going around in circles in the same direction in a flat plane, the same way as happens in our solar system for the same reason. What's the reason? First of all, of course, anything that's not going in a circle would collide with other objects, wouldn't really be very stable. But why is it spinning so much? Conservation of spin. It's up here, conservation of angular momentum. Remember, I showed the ice skater example. First, galaxies may start out as rather spherical blobs, but as long as that blob has a little bit of rotation, a little sense of rotation along one particular axis, as it gets smaller and smaller, it's closer and closer to the axis, it's going to spin faster and faster and faster until it's spinning at an orbital speed. So it can collapse vertically. It's okay for gravity to collapse things down into a very flat disk. But once they're spinning fast, it is not okay to collapse this way. You can't go to a smaller radius because that would violate conservation of angular momentum. This way, gravity squishes everything down that might be initially fairly spherical and slow rotating. Gravity is naturally going to squish everything down into a rapidly rotating flat disk. And that's what's happened to a large number of galaxies. There is an individual star in the constellation of Taurus, the stars forming in the middle there. It actually has also collapsed into a spinning disk of gas, and this is going to make new planets. Same basic idea there. I guess I just threw that in because I thought it was really cool. This course is not about planets. We're about much more exotic things than planets, but it is interesting that there are some similarities. Good point. Will is another point. If there was no rotation at all, suppose that the initial gas cloud was just sitting there with no motion at all, then you're right. It wouldn't spin unless something else passed by it and twisted it or something like that. And there are some galaxies like that that aren't really rotating very much. The things in the middle are on inside tracks. So the stars here will go around in less time. The stars out here are, it's a little bit like a racetrack. They're going around a larger path, and so they will take longer. So we're basically always kind of moving past the stars in the outer parts, but the stars in the inner parts are moving past us. And that can be measured with the Doppler shift. And a great deal of effort has gone into that. It's a little complicated because you have to remove our own motion to solve this. I'm just going to give you the answer here. I'm just going to tell you the result. The result is that the solar system, the sun and the planets going along with it, they're just carried along with it, goes once around in a circle, approximately a circle, around the entire galaxy about once every 200 million years. So you can see it's going at only about 1,000th the speed of light, because what, it was about 200,000 light years around, but it's taking about 200 million years to go around once. So that's not 1,000th the speed of light is not super fast. On the other hand, compared to stuff moving around here, what would that be? That would be about 300 kilometers per second. It's close to that. Okay. Anyway, so I'm not going to go into all of the trouble it took to figure this out, but I'm just going to use the answer now. Now we know in years what the period of our orbit is around the solar system. We know how big the orbit is, and I can put everything in solar units here if I just want to use Kepler's law. So in the units of the Earth's orbit, let's measure the size of the sun's orbit in terms of Earth years and astronomical units. So I just wanted to get the exact answer here. So if I put p squared in terms of years and r squared in terms of astronomical units, I get these numbers. You just have to really keep track of your powers of 10. I've got 9 times 3, I've got 27 powers of 10 up here, got about 16 powers of 10 down here. So most of that divides, and we get the answer 10 to the 11 in the units of the solar system, in the units of the mass of the sun. So now you know the answer. Within our orbit, and this is what's making us accelerate, this is why we go around, there's this much gravity from this much mass. 100 billion times the mass of the sun. That's a lot. It's not a complete shock because we've added up, if you try to count the number of stars that are in this region, there are billions of them. So maybe even tens of billions of them. So this is not a completely insane number here. It does seem to be a little bit on the large side, though. A little bit worrisome. Anyway, let's go a little further with this. Now, this is even a harder measurement to make. This is where things get really weird and strange. Let's see if we could measure what the orbital periods of gas clouds are, or stars, further out at larger distances, going around in larger orbits than we do. Then we could apply the same formula. We'd know how big their orbit is. We could figure out what their orbital period is, and then we could figure out how much mass is enclosed in a larger circle. This 10 to the 11, this 100 billion solar masses, is just what's inside the yellow circle. But with enough work and enough effort using Kepler's laws, we could draw bigger circles and figure out how much more mass is spread out in the Milky Way inside larger and larger circles. All right, what do you expect, by the way? You might say, well, let's suppose this is very simple. I mean, in this drawing, it kind of looks like, this is artist conception, but it looks a little bit like the picture I showed you of another spiral galaxy. It looks like most of the mass is concentrated in the center, doesn't it? That's where the starlight is brightest. That's where the density of stars is highest. How does that compare with the one other case that we've studied very much in detail, which is the mass causing the motions of the planets in our solar system? What's that situation? How is the mass distributed in our solar system, which causes the gravity that causes the motion of planets? It's almost entirely in the center, isn't it? Almost all of the mass. You can draw any circle you want. You can look at the orbit of any planet you want, Mercury, Mars, Venus, Earth, whatever. They're all going around pretty much the same mass. The mass inside the circle. This M in means the mass inside a circle of radius r. Well, in the solar system, M in is always just the mass of the sun. That's it. There's really almost no other mass, hardly counts for anything. There's almost no other source of gravity in the solar system unless you get really close to Jupiter, something like that. So what does this formula say? Just look at the formula here. The orbit, the speed at which a planet would go, if all of the mass was just concentrated in the center, like we were going around the sun, so that'd be a constant. That's the Newton constant of nature, of gravity, that's a constant. It should just drop as the circle gets bigger and bigger by 1 over the square root of r, and that's exactly what you see. So there's the Earth going around at, I don't know what that is, about 28 kilometers per second. That's what it takes for us to go around approximately in a circle in 365.25 days. Mars is going around in a bigger circle and it's going slower. I think I don't know if I went through this with you before. Saturn is going in approximately a 10 times bigger circle, but it's also going 3 times slower. Right? It's going the square root of 10 times slower. So that's how come Saturn takes 30 years to go around once around the sun compared to the Earth. And of course, Mercury goes around really fast. So if the Milky Way had all of its mass concentrated just at the center, if this was really just like a little scaled up solar system and all the mass was right here in the middle, then you'd expect to see the same thing. The orbital velocities should fall off the further and further you get away as you find objects that are orbiting further and further out from the center of the Milky Way. This is very important. Everybody see why that would be? Anyway, it's a bit of a straw man because I guess you all know that is totally not observed. In fact, that is never seen. It's not seen in the Milky Way. In fact, there is no galaxy really that's been measured carefully in the universe, and we're talking about thousands and thousands of galaxies and measured, where you ever see anything that looks like this. This is okay for the solar system, but clearly the assumption of what's in the solar system does not apply to galaxies whatsoever. So I still believe in Newton's laws. I believe in gravity. I believe that this formula is correct, but it just can't be that the mass is all concentrated in the center. That is so not wrong. In fact, it's kind of shocking what comes out. Here is the best reconstruction. And again, it was fundamentally using the Doppler shift, but you have to do a lot of geometric corrections. It's a pain in the butt. We actually spend a week or two in Astro 140 when the Astro majors work this out. But anyway, you see the orbital velocity in our galaxy. Here's what the sun is doing at that speed, does not change with the size of the circle. It doesn't really matter how far you are away from the center. Here's the center of the Milky Way there. Like I said, we're 25,000 light years out, but you could go 50,000 light years out. Now, these are extraordinary measurements. These are hard to do. You could even go 75,000. There's not much out there. But if you could find some gas that's moving around in a much, much larger circle, 75,000 light years out or whatever, it's still going around at about the same speed, the same velocity as we are. In other words, if you plot the orbital speed as a function of the size of the circle, as a function of the distance from the center of the Milky Way, that's often called a rotation curve. It shows the speed of rotation. It's flat. V is a constant. V does not depend on R. See, so V squared doesn't depend on R either. It's independent of R. You can see that it's pretty independent of R. Well, V squared, which doesn't depend on R, is just G M inside divided by R. So what's the conclusion? You got to look at this formula. I might actually give you a 3-point question on this. If this is constant, it's independent of R, this can only be satisfied if there's a very simple but shocking, very surprising relationship between the enclosed mass, that's the mass inside, I put bigger and bigger circles that you draw around the center of the Milky Way, the enclosed mass increases in direct proportion. So if you double the circle, go from 25,000, remember from 25,000, we said that we were enclosing 10 to the 11, 100 billion solar masses. If you draw twice as large a circle, go out here to 50,000 light years, that goes up by 2. The mass also doubles. Whoa, it doubles. So that would be 200 billion solar masses. If I went out to 3 times as large a circle, out to the amount of mass enclosed within 75,000 light years of the Milky Way, it's 300 billion. The mass just keeps going up the bigger and bigger the circle is that you draw around it. That should really disturb you. That should be shocking. And the reason it should be shocking, the amount of visible matter that you can see, the stars, is not going up that much. It's largely concentrated in the center. In fact, as you get to these outer portions, there's almost no visible stars at all. So I'm talking about, really on this scale, I'm talking about drawing a circle out to here. And we're saying that there's twice as much mass in it as inside this circle. If I go out to here, it's a huge circle. Doesn't seem to be hardly any stars out there at all. But I'm telling you, gravity is telling you, Newton's laws are telling you by measuring orbital periods, orbital velocities, there's 3 times as much mass enclosed out here. So by the time you get to the outer parts of the galaxy, there's an outrageous discrepancy, a complete disagreement between the amount of gravitational mass, which we know must be there because it's causing the acceleration. It's causing these flat rotation curves. It's completely discrepant and not agreeing at all with the visible mass of stars that you can see. So that leads to my conclusion at the bottom of the slide here. If you add up all the mass of a spiral galaxy, this actually applies to other galaxies too that are rotating, even if they're not spirals. You add up all the mass in the outer parts. The outer parts are mostly invisible. The outer parts are not stars. The outer parts are not producing light. All they're doing is producing gravity, which causes these large velocities. The outer parts of galaxies are spinning or rotating way much too faster than they should have been if you just had visible matter of stars to account for it. So most of the matter is in an invisible form. It's there. We used to call it missing mass, but that's a complete misnomer. Sorry. The mass is definitely present there, but it's dark. You can't see it, and nobody has really managed to see it with any measurement of any radiation at all. So it's the dark matter. And the shocking thing is that if you include a large circle around most galaxies, there's much more mass in the dark matter than there is in the visible stars. The visible stars are sort of like the tip of an iceberg. Galaxy is kind of like an iceberg. The visible part is really only the little part that's above the surface of the waterline. Most of the mass of the Milky Way and all these other galaxies is invisible and is extended in an enormous invisible halo. Isn't that shocking? So this is not the Milky Way, but it's another example here. You measure the orbital speeds of gas further and further out in this beautiful spiral galaxy here, and they never go down. It's pretty flat. This is actual data. This is real data. You can see the velocities don't go down. So that means the total amount of, on one side it's blue shifted, yes, and the other side it's red shifted. That's one part is coming towards us, one part is going away from us. But the fact that the velocities, the orbital velocities, continue to be very high this far out proves that there's a tremendous amount of unseen or dark matter in most galaxies. 90% of all the matter in them. All right. Just to show you, just to hammer this home, here are the rotation curves of a bunch of nearby galaxies that have been measured. We measured these things out hundreds of thousands of light years from the center, and they still keep on going flat. Nobody's ever found the edge of these galaxies. Yes, there's an edge to the stars. The starlight has practically gone away. But if you're able to measure some thin little amount of gas or something orbiting, the mass just keeps on going up, and the enclosed mass keeps on going up and up and up. So all galaxies live in enormous, gigantic dark matter halos, which really dominates their mass, except in the center. All right. So I think I said all this stuff. This is one of the biggest discoveries of the second half of the 20th century. So I kind of wanted it to be in this course. Because now we're telling you what most of the universe is made of. And so it's useful to know that fact. For example, if you want to figure out how the universe is going to move, if you want to figure out stuff about cosmology, what is the dark matter made of? Well, of course, Will has an excellent question there. I'll give you the simple answer. We really have no idea at all. It's crazy, isn't it? So you'd have to say that that would make that automatically one of the biggest questions of modern physics. What's most of the universe made of? I don't even know what kind of particle it is. I can tell you one thing, though. It's not made up of neutrons, protons, and electrons. It's not made up of what we're made up of, which I thought was normal matter. How can I say that? I'll give you multiple pieces of evidence that it's not normal matter. Weird. We're always biased, that we're the most important thing. And so we're not only are we not at the center of the universe, we're not at the center of the solar system, God, we're not at the center of anything. We're not even made up of the stuff that most of the universe, 90% of the universe, is made up of. It probably the best money bet, but it's not been proven at all, is some kind of particle that really doesn't make light, that has only weak interactions. Something like maybe a neutrino, although that is a dark matter particle, but it's been ruled out. It's not the explanation. Some other particle that it has to have mass, because you need a particle to have mass to produce gravity. It probably has no normal interactions, only weak interactions, and it has not yet been discovered by modern science. It remains to be discovered. Man, there's an instant Nobel Prize, the person who discovers the particle of which most of the universe is made of, but we do not know what it is right now. Amazing. It's incredible. All right, so there's my little, galaxy. Here's all the stars there and everything. That is just the tip of the iceberg. That's the normal matter, but there's this unseen halo, and this is somewhat to scale, actually, that is so huge it probably extends almost until you get to the dark matter halo of Andromeda. Andromeda is a nearby galaxy. It has a dark matter halo also. All right, so the galaxies are spinning too fast. All right. So that is such an outrageous claim that obviously you would want to confirm it with some other supporting measurements. So I'll just mention the idea. Could we play the same game? Because astronomers love to play the same game. Could we watch galaxies orbiting around other galaxies? Right? We watched planets orbit around the sun. Then we watched the sun orbit around the Milky Way. Now, could we find a whole bunch of galaxies together in a cluster orbiting around their common center of mass? Then we measure how fast they're going. We measure what their acceleration is, and then we work out what the total mass of the galaxy cluster is. Sounds like a good idea? Yeah, it's the fact that the same way that stars are generally not isolated, they form around other stars. They come in these large concentrations, star clusters, and galaxies, which are huge concentration stars. The same is to some extent true of galaxies also. Galaxies like to be together. They're kind of social. If you find one galaxy, you're much more likely to find other galaxies nearby. And then there are some regions of the universe that are like empty of galaxies. Anyway, in fact, we ourselves are in a group of galaxies with Andromeda and a few other dinky galaxies, such as the Large and Small Magellanic Clouds, a few other galaxies that you haven't really heard of, and so on. And it's a group of galaxies, there's a few dozen of them. It's called the local group. That's a very imaginative name, isn't it? But actually, the local group of our galaxies is really on the edge of a big cluster of galaxies, which is centered in the constellation of Virgo. It's in the direction of Virgo. And that has thousands of galaxies in it, and we're on the edge of it. And that's quite typical. Again, nothing special about where we are. I love these. These are some, I'm going to show you some even better slides of galaxies. Almost everything in this picture is fuzzy, and it's a galaxy. These are honking huge clusters. Same for this one. There's a few foreground stars in the Milky Way, but almost everything here is a galaxy in a cluster. There are thousands of them. So all we have to do is see how fast they're moving around. They're on sort of random orbits around the center. So we can just measure the average Doppler shift, the average velocity, and figure out what's the average mass of these galaxies, or what's the total mass of the cluster of galaxies. All right, so should work. I mean, remember, I've never questioned Newton's laws or Kepler's laws. I've never questioned that is also the cause of these galaxies orbiting around at high speeds, because I really can't question that. Well, if I don't question that, then there's just loads of dark matter in these galaxy clusters. They're just filled with it. All right, there's another beautiful example. Anyway, it's even worse. There's so much missing mass that's not accounted for. Yes, I know there's a lot of starlight. You can see all the starlight here. That's a heck of a galaxy cluster, isn't it? This is much bigger than our Virgo cluster. This is 5,000 or 10,000 galaxies clustered around here. Most of the mass, though, is not visible in this picture at all. About 95% of the mass is not in stars in this picture. My goodness. And that is typical. This was pointed out actually in the 1940s. I mean, a guy named Zwicky, who had a terrible personality and no one would listen to him, and he hated everybody and the feeling was mutual, actually made this discovery. And I think it was ignored for like 30 years because of his personality. But he said these galaxies are moving at crazy high speeds. If it was only the mass of the stars, if that was all the gravity that was here, it wouldn't be enough to hold things together at such high speeds. At these high speeds, all of the galaxies would have escaped millions of years ago. It would have escaped immediately, but they're not escaping. They're held together. These galaxies clusters have held together for billions of years because there's so much more dark matter present in these clusters. So just the crazy high speeds, it's a little bit similar to the crazy high speeds of orbits that we've noticed in the outer parts of the Milky Way galaxy. Now we're seeing the same thing in ensembles of thousands of galaxies, crazy, unexpectedly high speeds. Again, telling us that most of the gravity is missing matter. Okay, dark matter made of, how big or small can galaxies be? What an interesting question. Galaxies do come in all sizes, right? Those dinky little clouds of Magellan are just like a few percent of the Milky Way. And those are very common, right? It's always true, right, in the universe. The little small things are the most numerous. But there are some spectacular galaxies like these here. These are much bigger and much brighter and much more massive by a factor of 10 than the Milky Way. So the Milky Way is kind of in between. Why the galaxies are all the different sizes they come in is an interesting question, which has not been entirely explained, but it must have something to do with dark matter. Because I'll just put this out and then we'll quit. The formation of galaxies can only happen from the gravitational attraction of dark matter. If it were not for dark matter, there is no way that we would be here right now. It's absolutely essential for creating galaxies. Couldn't do it without it.